In this presentation, we're going to look at the Newton-Raphson method, and just as an aside, don't take I say Newton-Raphson, but that's not a definitive way to pronounce it. I'm open to correction. Consider the equation e to the power of x plus 2 minus x squared plus 3x equals 0. Use the Newton-Raphson method to find the solution with a precision of 3 decimal places, taking an initial guess x0 equals 0. Now this is the formula we're going to use here, and it's an iterative formula. And what we do here is construct the next solution based on the next approximation based on the previous one. So for example, we have to compute x1, and that is x0 minus the evaluation of the function at x0 all over the evaluation of the derivative of the function at x0. Okay, so what we have to do here is actually just recall our function here. E to the power of x plus 2 minus x squared plus 3x. So what we have to do is get the derivative of that, and this is straightforward enough. E to the power of x plus 2, well, that's the same as e squared, which is a constant, times e to the power of x minus x squared plus 3x. Okay, this part here is a constant, so we just ignore that. E to the power of x, the derivative of that is itself. So this part here we don't do anything with, so we leave that alone. So it actually e to the x plus 2, just leave it back as it was. This next part here, minus x squared, the derivative of that is actually, let's just use the notation here, f of x and f dash of x. And that is 2x, that's the derivative of x squared. And now let's get the derivative of 3x, that's just 3. Okay. So, okay, let's evaluate that at both of them at 0. Oops, gone too far there. These are other presentations. Let's go back there. So x to the power of 0. We're just told in the first instance use 0. Then we evaluate f of 0. Okay, I'm just going to give the answer here. 7, we're told to use to 3 decimal places, so let's just use a couple of more. So we have, my calculator is giving me 6 decimal places, so I'll just use that. If we evaluate f of 0 out, there, that's what I get, e to the power of x plus 2. And let's evaluate the f dash of x, or the derivative of f of x, and I get this 0.938 1.0389056. Okay. So evaluate like that. Now this is not a very, how should I put it, useful way to continue. It's just I'm sort of setting it up. If we just use those values there to calculate x of x1, that's simply 0 minus 7.389 divided by 10.389. Actually, I'll use all the decimal places I was using. 0.56. We get an answer of minus 0.711. Well, actually, I've got a few more decimal places here. But what I want to do is actually sort of what I've just done there is just to sort of get the ball rolling, but we have to use a bit of more of a systematic approach here now. So I'm going to sort of go to the next slide here, and what we're going to do is set up a little table. Okay, n, and we're going to have our x of n here. I'm going to have f of x of n and f dash x of n. So the example, the sort of work I've done here in the last slide here is just a sort of quick, sort of rough work example of how I calculate the next value. So the current value, x of 0, minus the evaluation of f, which we have 7.389056, divided by the evaluation of the derivative of f, and that is 10.389. And that gives us the answer for the next iteration. So let's just start that here. 1, 2, 0, 1, 2. The first trial, the solution there was 0. We got 7.38956 and 10.38956 here. And we found that the next iteration was minus 0.711235. Just give it all 6 decimal places. Now we're going to evaluate this 0.711235 in our function here. And what we should get out after a bit of calculator work is 0.9888746. Okay, just to be clear, where does that come from? That 0.9888746. Let's go back here. If it's what happens when I put in minus 0.71 plus 2 minus 0.711 squared plus 3 times 0.711. I'm only using 3 decimal places there just because of the sake of how much screen space I would use. So essentially just evaluating like that, and likewise to find the derivative, the value for the last column, evaluate this as well with x equal to minus, sorry, it's a minus there, x equal to minus 0.711. I've gone too far there again, sorry. When we evaluate the last column there, something very similar, we get 8.05073. Now it works out the same way. So what we're going to do is minus 0.711 minus 0.988 divided by 8.053. Let's just have a quick look at that. Minus 0.711 minus 0.988 divided by 8.050. Okay, and working that out, we would get minus 0.834048. Okay, now I'm going to sort of cut to the chase here a bit. If we evaluate the whole thing out again, what would happen here is we get the following numbers here. I'm actually just going to, I'm going to sort of stop explaining my work, my rough work now, just for the sake of time. And I'm just going to give the evaluations here. So when we evaluate this value here evaluate the function f with this input here, 0.834048, 834, we should get 0.011193. Evaluate the derivative of f at minus 0.834048. We should get 7.877072. Okay. Using those three values to evaluate the next trial solution, we will get 0.835469. Now, I'll just draw attention that this number here, 0.83 minus 0.834 and minus 0.835, are pretty close, but they're not close enough to 3 decimal places. So we have to keep going. So evaluate that, we get 0.00001. Oh, that looks pretty promising. Evaluate this, we get 0.877. No, we don't. 0.875357. And working that out to get the next iteration, we get minus 0.835470. So we can stop here. The reason is we are getting the same answer the first 3 decimal places. So that means that we are close enough, essentially. So that's the Newton-Raphson method. It's a lot of number crunching once you get the hang of it, it's grand. I'll call it a day.